My name is Yu Yang. I'm from Rutgers University. So today it's my great honor to present our work, which is a system called VeMo to enable transparent vehicle mobility modeling. So this is a joint work with SIAT and USTC. So actually I'm from the same group of our previous speaker. So our work is about vehicle localization. So this kind of thing can enable a lot of real-world applications, such as the connected autonomous vehicle and the traffic emergency response, and also the vehicle location-based services. So given all these applications, our question is that, so can we infer the locations of all the vehicles in a given road network? To answer this question, we conduct a field study in an expressway system. So for an expressway system, so any vehicle gets into the expressway need to pass the toll collection stations. So after this, our goal is to infer its real-time location in any given time before the vehicle leaves the expressway. So not only concerned about one vehicle, we actually are concerned about all the vehicles entering the expressway to know their real-time locations. So we can categorize the previous work into a two-dimensional table according to two principles. So one is the sensing approach, if they use mobile sensing or stationary sensing. So another dimension is the objective. So if they care about the individual result or the aggregated result. So in our work can actually fit into the last cell, so which we utilize a ETC station, the ETC system at a concrete stationary sensing system to infer the individual vehicle's real-time locations. So there is several challenges to implement this. So for a simple example, in order to localize a vehicle, so if we know its destination, route, and speed, then it becomes a straightforward problem to address. But actually in our system, we find all these three elements have a great uncertainty. So for example, for the destination, from our study, we find giving an arranged station, so each vehicle may have more than 4 different destinations to go. Even we can solve this, we find the route is still uncertain here. So in our system, we find, so for each arranged destination pairs, so that each vehicle can, so this problem becomes even worse when it's in expressway. And further, the vehicle can move at different speeds in the highway, which also introduces another uncertainty here. To address these challenges, we designed a data-driven system consisting of 3 key components. So the first one is the data. For the data part, we utilize a roadmap, the context information, and also the ETC billing data. For each record in the ETC billing data, we have the vehicle ID and the origin stations and time, and the destination stations and time. So here we do not have any GPS traces from the vehicle. Given this data, we extract different features from 3 perspectives, which lead to our 3 different predictors to address the 3 uncertainties here. And then in any given, in the real time, when a vehicle get into the expressway, we first predict its destination and also its driving route. And then in real time, we want to infer its driving speed, which finally gives us the inferred real-time locations. So this seems a complete system, but we miss one important component here, so which is the training label. So as we all know, for any supervised learning model, we need a training label to train our model. So let's say if our data can support us with this. So for the destination predictor, we can simply obtain its destination label from the ETC data already, since it's already collected. But for the route and speed, since we do not have any detailed GPS traces for the vehicle, so it's hard for us to obtain the historical route and speed as label to train our predictors. So in the next slide, I will especially focus on this problem. So how we utilize the ETC data only to infer the historical route and speed to perform as our training labels. So to answer this question, I will give a simple example here. For example, a vehicle gets into the expressway at 8 a.m. and leaves the expressway at 9 a.m. So in this way, we know its travel time is around 1 hour on the expressway, and there are possible like 2 roads between them, and the vehicle can drive at different speeds on the road. So so we find that both the route and speed, they work together to determine the travel duration. So that means there is a strong relationship between the travel duration we observed and the route and speed they choose. So then we conclude our problem as, so if we can find a combination of the route and speed that can maximize our observation of observing the travel duration. For example, if we can find in this example, if we can find the route 2 and the driving speed at different route segment to maximize our observation of the 1 hour travel duration. So not only about one specific ETC record, we care about all the ETC records generated from our system. So basically, this gives us the problem formulation here. To address this formulation, we utilize an expectation maximization algorithm, and the details can be found in our paper. So now let's switch our gear into the evaluation part. In our evaluation, we conduct a large-scale experiment in a province with more than 8,000 kilometers expressways, and in this system, we have more than 1,400 stations. And the ground truth is given by the real-time GPS location of vehicles installed with OBD devices from an insurance company. So in real time, around 10 to 15 seconds, these vehicles upload its real-time GPS coordinates. And also this figure shows the heat map of the trajectories of these vehicles. So we can clearly see some high-density area, which are the major expressway in the province. And in the real-time implementation, we split our ETC data into two parts, the training part and the testing part. In the training part, we train our 3 different predictors. And in the testing part, given any real-time entries of the vehicle, we want to predict its real-time locations. And then we compare our prediction with the ground truth obtained with the actual location obtained from our ground truth to know if the vehicles are falling, if the prediction is falling into the 100 meters of the actual location. So this also gives us the definition of the accuracy. So the reason I'm choosing 100 meters is because the uploading frequency is around 10 seconds, and the GPS error may around 10 meters. So now let's see some result here. So we first give the comparison between our work and a surveillance camera network-based solution called S-Track. In this baseline, we introduce around 500 cameras in the major road segment in our city. So we assume the vehicle's location is known if it's captured by the camera. So we find our system can actually outperform this baseline. And then we introduce another baseline, which is a cellular network-based system, which is called C-Track. In C-Track, we utilize around 3,000 cellular towers in a city to infer the locations of the vehicles. So actually, we find C-Track has a better performance than us. So we dig into what's the reason for that? We find if we cannot predict the route very correctly, so then the performance will decrease. So to show that we narrow down our result into the prediction with correctly predicted route, then we find, given this condition, we find our system can actually has a better performance than the C-Track. So we also done some other evaluation on some intermediate results, such as the destination route and speed for each individual predictor, and also some impact factors like the weather, area, and vehicle type. And finally, I want to conclude my presentation with 3 takeaway messages. So the first is about the benefits of ETC sensing. Since the ETC data is originally collected for bidding purpose, so in this way, if we utilize it for localization, then we do not introduce any other extra deployment. So this is actually transparent to all the drivers. And also it has better privacy prevention, since we only expose very limited location information of the vehicles when they get into the expressway and leave the expressway. And also the key problem in our system is to find the historical labeling of the route and speed. And also if we can solve this, we can achieve a competitive performance to the densely deployed infrastructure solution. And finally, our system can also be generalized into other similar situations, such as using stationary sensing as the sensing approach to get some individual result, such as the intelligent edge cameras in our city. So, and also we release some of our data in the website. Welcome to check that. So with this, I'm happy to answer your questions. Thank you.
Thank you very much.